All right, welcome back to another calculus lecture. In today's lecture, what we're going to do is show how you can use just a function and nothing but its derivatives and a little bit of reasoning to actually sketch a pretty good picture of the graph using no software whatsoever. So all we're going to do is actually just look at a function, look at its derivatives, analyze them using the techniques that we have up to this point, and then we'll actually be able to sketch a graph using that information. So let's go ahead and just dive right in. We'll just do one example for this lecture because it'll actually take us a fair bit of time. So let's let f of x, and the example I've chose is the function 2x squared divided by x squared minus 4. And what we want to do is sketch a graph that is using no software or anything like that. Sketch a graph of f of x. So that's our goal. So what do we need to do? Well, we're going to need the first and second derivatives, so we might as well just go ahead and compute those. And for the sake of time, I'm just going to write down what they are. You could certainly go through and compute these using the quotient rule, but the first and second derivative are given by negative 16x divided by x squared minus 4 quantity squared, and then f double prime of x is going to be equal to 16 times 4 plus 3x squared over x squared minus 4 quantity cubed. Okay, so these are the first and second derivatives. And in order to sort of sketch a graph of f of x, we need to sort of summarize the information that we need. So I'll go ahead and maybe write out a list of everything that we'd like to know in order to sketch a graph. So things we need to know. So firstly, we need some values at a few points at least, just to give us an idea. We don't need values at every point because then we would just have a graph. But we need values at a few points just to be able to orient us of where our graph is. We would like to know the intercepts of the graph, so where it crosses the x and y intercepts, where it crosses the x and y axes. So we need to know the x and y intercepts. That is the y-intercept and the zeros of the function. We would like to know if it has any asymptotes, vertical or horizontal. So vertical and horizontal asymptotes. And this information we can all get from just the function. So we don't need to know anything about derivatives in order to get these first few pieces of information. The thing that we do need the derivative for is we'd like to know critical points and extrema, so local maxes and local mins. We would also like to know where the function is increasing or decreasing, and that sort of ties in with knowing whether or not you have a local max or a local min from the first derivative test. So I'll just say increasing, decreasing. And that's pretty much everything we can get with the first derivative. And the second derivative is going to allow us to know where the graph is, well, maybe we'll say inflection points, which is where the concavity switches. And then we need to know the concavity of the graph at various places. So all of this information we have already seen in various lectures, how to actually get this information. So now what we're going to do is actually, for just one function, get all of this information, and then we're going to use that information to sketch a graph of f of x, and then we'll see what it actually looks like and see how close we got. Okay, so let's just dive right in. The values at a few points, we'll come back to that and maybe do that at the end, just so we know where our points of interest are. X and Y intercepts, so maybe we'll just do an enumeration here. So A, we'll do the x-intercepts first. So the x-intercepts, I want to figure out where the function is equal to 0. So x-intercepts are all the values of x for which this is true. Well, if I have a rational function, 2x squared over x squared minus 4, this function is only 0 when the numerator is 0. So only need to check where the numerator, 2x squared, is equal to 0. And it's equal to 0 at 0. And it's the only point where it's equal to 0. Okay? Now for the y-intercepts, the y-intercept is really easy to get. All you do is just substitute the value 0. So f of 0. Well, we've already seen that. If I plug in 0 here, x equals 0, it makes the function equal to 0. So f of 0 is 0. And this tells us that the only intercepts we have is just at the origin. It's where the graph sort of is crossing either of the axes. It happens to be in the same place. This doesn't always happen, but it certainly does in this particular example. So there's that. Now let's move on. Let's do the vertical and horizontal asymptotes. We'll do vertical asymptotes first. So for the vertical asymptotes, what I need to know is where the denominator is equal to 0, because that means that the function sort of blows up at that point. So I set x squared minus 4 equal to 0. And this pen is running out of ink, but I have another one right here handy. So x squared minus 4 equals 0, and we could factor this, or we could just, do a little bit of algebra. So x squared is equal to 4. I add 4 to both sides, and then I take a square root, and remember that if I take a square root, I have to take both the positive and the negative square root. So this tells me that x is going to equal plus or minus 2. So those are where I have vertical asymptotes. Okay? Now let's do the same thing for the horizontal asymptotes. And remember what horizontal asymptotes were back when we were computing limits and things like this. Horizontal asymptotes were where we had a limit at infinity. So we need to compute the limit as x goes to plus or minus infinity of x squared, 2x squared over x squared minus 4. And if you remember, we had that theorem that told us how to evaluate limits like this. So to evaluate this limit, it's enough to look at the leading coefficients of each of these polynomials. We have 2x squared on the top, so I have a degree 2 polynomial in the numerator, and likewise I have a degree 2 polynomial in the denominator. So what this tells me is that my limit is just going to be equal to the ratio of the coefficients of the leading order terms, which is just 2 divided by, and then there's a 1 right here that we didn't write down, but this is just going to be 2. And it doesn't matter if I go to positive or negative infinity, the answer is going to be the same. Again, that doesn't always happen either, but in this case it happens to happen. That was the dumbest sentence I've ever said. Anyway, so there's all the information that we can get with using just the function itself. Now let's maybe look at the information we can get from the derivative, and I've run out of room here, so let's go ahead and just turn the page. So let's go ahead and get the critical points. And the critical points are the points in the domain of the function where the derivative is either 0 or undefined. So in our case, we have the derivative, so f prime of x. This was and I'm going to turn back real quick just to make sure I don't get this wrong. Yeah, negative 16x divided by x squared minus 4, quantity squared. This function, well, if I think about where it's 0 and where it's undefined, it's certainly undefined at x equals plus or minus 2. We sort of already saw that with the regular function. But x equals plus or minus 2 is not actually in the domain of my function, so it's not going to be a critical point. However, it will be a point that I need to consider when looking at intervals over which the function is increasing or decreasing. So what this tells me is that the only critical points of f prime of x are going to be where its derivative is equal to 0. And just as we did before, it suffices to just check where the numerator is equal to 0. So set that equal to 0. This means that negative 16x is equal to 0. And then, of course, this just tells me that x equals 0 is a critical point. So it's my intercept, the x and y intercept happens at x equals 0. And I also happen to have an extrema there. Now, we have the first derivative test, so we can certainly classify whether or not this is a local max or a local min, or neither. That's potentially true. But that information is sort of going to come about from the next thing that we look at. So let's look at where the derivative is positive or negative, that is, where the function is increasing or decreasing. So increasing versus decreasing. So in order to figure out where the function is increasing or decreasing, I need to know all the points at which it can sort of transition between those two. Well, it can certainly happen at critical points, but it can also happen on either side of a vertical asymptote, or these points where the derivative and the function are undefined. So let's go ahead, and what we'll do is make a sign chart with all of the sort of transition points or points of interest for the first derivative. So if I do this, we'll have negative 2, 0, and positive 2. And then I can do the same thing that I do with the first derivative test and just pick convenient values in each of these intervals. So remember, these are defining intervals, so negative infinity up to negative 2, and then negative 2 to 0, so on and so forth. So we just need to pick a convenient number in each of these intervals. So we'll just do negative 3, negative 1, 1, and 3. And then we need to evaluate the first derivative at these points. So if we do that, here's my first derivative, f prime of negative 3. Well, I don't really have to evaluate the entire derivative. I can just sort of think about what its sign is going to be. So if I plug in a negative number, well, the denominator is a square of a number, and if I square any number, it's always going to be positive. So the denominator here doesn't contribute to the sign of the first derivative. So the only thing that is going to govern the sign of the first derivative is the numerator. So if I have a negative 16 times a negative 3, I'm going to be negative, or I'm going to be positive. So a negative times a negative is going to be positive. Likewise, same thing happens. I'm going to be have a positive first derivative at negative 1. And then the opposite things happens on the other side of 0. So I have a positive 1 times a negative 16, so I'm negative, and then same thing for 3. So f prime of 1 and f prime of 3 are both negative. And now what we can do is we can sort of do our thing where we put in roughly what the picture of that looks like. And we know now that the function is increasing. It has a positive derivative from negative infinity up to negative 2. It's not increasing or decreasing at negative 2 because the function isn't defined at that point. After negative 2, between negative 2 and 0, I am again increasing. And then I switch at 0 to being decreasing. And then same thing, I'm decreasing on the other side of positive 2. So this tells us the intervals over which we're increasing and decreasing, and that's pretty much everything we can do with the first derivative. So lastly, maybe let's go to the second derivative and see what we can see there. So we do the same sort of procedure, and we're going to figure out if there are any inflection points, and then figure out the intervals of our concavity, or where we're concave up and concave down. So inflection points. So the second derivative, remember, was 16 times 4 plus 3x squared over x squared minus 4 quantity cubed. And the inflection points, just like with critical points, the only points where you can have an inflection point is where the second derivative is 0. Well, if I think about where this thing can be 0, again, the same thing happens where the zeros are governed only by the numerator. Well, notice what happens if I look at this numerator. Let's just set this equal to 0 and solve. So 16 times 4 plus 3x squared is equal to 0. Well, let's rearrange this. If I divide by 16, I get 4 plus 3x squared equals 0. And then I subtract 4 and divide by 3, and I have x squared is equal to negative 4/3. So I subtracted 4 and then I divided by 3. But x is a real number, and the square of a real number is never negative. So there are no inflection points. And likewise, there are no other points where this happens. The inflection points only occur at the critical points of the first derivative. So just like the zeros of the, or where extrema occur at the critical points of a function, the inflection points occur at the critical points of the derivative of that function. So the second derivative here has no zeros, and there are also no points where the derivative where the second derivative is undefined that are in the domain of f of x. So there are no inflection points here. However, just like with the critical points, we are going to need to consider these two values that make the denominator 0 when we go to decide the intervals over which we're concave up and concave down. So lastly, concavity. We're going to do the same thing that we did before, and in fact, we're going to use pretty much the same numbers, except 0 doesn't play a role here now. 0, we didn't do anything with that here. So for concavity, again, we draw our little sign chart, -2 and +2, and we'll pick convenient values. This time we can use the value 0, just because it's nice and convenient. And we evaluate the second derivative at each of these points. So f double prime of -3. Well, let's go ahead and plug that in. This is going to be I'll just do this off to the side here. If I was better prepared, I would have just computed this before, but we might as well do it here. So I'm just plugging in -3 and doing the computation. And really, I only care about the sign, so I may not finish this whole thing, but notice what I have. I have 16 times 4 plus -3 squared is 9 times 3 is 27, divided by -3 squared, again, is 9 minus 4 is 5. And at this point, I can see I have a positive number. So we'll just go ahead and write positive. If I plug in 0, then I can do that fairly quickly. I'm going to have a positive number up in the numerator, and then I'm going to have a -4 cubed in the denominator. So a negative times a negative times a negative is going to give me a negative number. And so the second derivative in this interval is negative. And likewise, the same computation for -3, you just remove this negative. It's going to tell you that the second derivative is positive to the right of 2. So we have plus, minus, plus. Okay, so this tells us that we are concave up to the left of -2 and to the right of +2, and in between those two values we are concave down. Notice what kind of extrema I have at 0. I'm increasing and then I switch to decreasing, so I have a local max here, and the second derivative test tells me that if I'm at a local max, my second derivative should be negative, and indeed that is what we have happening here. So nothing too surprising there. But yeah, this is pretty much all the information that we need in order to graph our function. So maybe let's get some extra points here. I forget what bullet point we left off on. H. So we'll do I now. So we already saw that something interesting happens at 0, and we know that f of x is 0 at that point. We know that it's undefined at -2 and +2. And maybe let's go ahead and just get a few more values. F of 1. So this was 2 times 1 squared over 1 squared minus 4. And then notice that I actually have an even function. All my powers of x are even. So the function is going to be symmetric about the x and y axis. So f of 1 is going to equal f of -1. And this is going to be, let's see, 2 over -3. So this is just -2/3. And then we'll do f of 3 maybe. 2 times 3 squared over 3 squared minus 4. This is 18, so 2 times 3 squared is 2 times 9, which is 18. And then I have a 3 squared, which is 9, minus 4, which is 5. And then maybe real quick we can give sort of a decimal approximation of these. And then 18/5 is going to be, what is this, 3.6? It's actually equal to exactly 3.6. And I think that's enough information. So let's go ahead and try to graph this. So we'll get a nice big axis on here. So here's my x-axis. Here's my y-axis. And we'll just put a few tick marks on here. We'll just let each of these be 1. Again, we're just sketching this. We don't have to be super sort of accurate about this. So let's go ahead and, in order, place our information on the graph here. Maybe we'll go ahead and put these points in too. We did those last, but we'll graph them first. So we know that our intercept was at the origin, so 0, 0. We know that we have vertical asymptotes at +2 and -2. So let's draw those in. So there's the one at -2. Here's the one at +2. We also have a horizontal asymptote at +2. So that was right here, the y equals +2. We can go ahead and put these points in. So at at +1, we're at -2/3. So maybe somewhere right there. And then the same thing happens at -1 because we have an even function. At f of 3, we're at 3.6. So maybe something like this in between 3 and 4. And now, let's see, so that's our intercepts, a few points on the graph, horizontal and vertical asymptotes. Now let's go ahead and put in our critical points. Well, we had the local maximum at 0, and I know that my function is increasing, increasing, decreasing, decreasing on either side. And now I just need to use my information about my second derivative. So I know that I was concave up, concave down, concave up, and so this tells me that my graph should roughly look like this. So I have to be concave up here. I can't be sort of concave down at these 2 points. And then in the middle here I have a maximum, so I should do something like this. Doesn't have to be perfect, but I would just show that those points are on the graph. And there we go. We've got a rough sort of picture of f of x. And we're done. That's all this sort of interesting information. The picture continues sort of as you would expect it, down this way, up this way, and up or down this way. So we're really sort of done at this point. So let's go ahead and check to see how close we got. So if I graph this in Mathematica, then you can see, okay, here's my vertical asymptote at -2 and +2. Here's my horizontal asymptote at, there we go, cursor was invisible. So vertical asymptotes here and here. I have my horizontal asymptote at y equals 2. This is 5 right here, so 1, 2, 3, 4. So there's my horizontal asymptote. Here's my local maximum at 0, and it's also my intercept. And then I am concave up and increasing, concave down, increasing, concave down, decreasing, concave up, decreasing. And this precisely agrees with the information that we had before. So if I sort of switch back and forth between these two, I'm no Picasso, so this is not, amazing, but it's at least pretty close. And this is sort of one of the really cool things about calculus is you can do this completely analytic process. You don't need to know really anything about the function a priori, and you can deduce all of this and get a pretty good idea of what your function actually looks like. Okay, so that's everything I wanted to do for this video. Normally, in a usual calculus class, I'd put this on an exam and have like a 8-part question that had you compute all this information and then use it to get a picture. It's not really feasible for an online class because there's no way for me to stop you from just looking at a graph. So whenever I, quiz you guys on this stuff, it'll mainly be on some of the, individual pieces, like where is a graph concave up or concave down, things like this. Okay, so see you all in the next lecture.